Our next experiment deals with the phenomenon of second sound. We are all familiar with wave motion in elastic materials, be they solids, liquids, or gases. Elastic energy of deformation carried away from a source in the form of waves with a characteristic speed, the speed of sound. Liquid helium is an elastic substance, both above and below the lambda point. Both helium-1 and 2 support sound waves. Now, helium-2, the superfluid phase, also conducts heat in the form of waves. This remarkable property is shared by no other substance. For better or for worse, it has been called second sound. Normal heat conduction is a diffusion process. The rate of flow of heat is proportional to the temperature differences. But in helium-2, it is a wave process. Heat flows through helium-2 with a characteristic speed, the speed of second sound. We shall send small heat pulses into helium-2 from a heater. They will spread away from the heater uniformly, carrying the heat energy with them. The speed of second sound is small, just below the lambda point. In the neighborhood of 1.6 degrees Kelvin, it reaches a value of roughly 20 meters per second, and it is in this range that we will run our demonstration. The experimental procedure is as follows. There are two disks in the liquid helium. They are carbon resistors, with the carbon applied in thin layers on one side of each disk. In this way, good thermal contact is established between the resistor and the liquid helium. The bottom resistor will be used as a heater. Electric current will be sent through it in pulses from this pulse generator by means of the cable you see here. The output of the generator is also connected via a second cable to a dual trace oscilloscope, where it will be recorded on the bottom tray. In other words, it will record the heat pulse as it enters the liquid helium. The pulses have been turned on. They themselves trigger the horizontal sweep of the trace, which records time elapsed. It is calibrated at 1 millisecond per unit on the scale. The pulses are 1 millisecond long. The pulses leave the heater at the bottom in the form of second sound and move up to where they strike the carbon resistor at the top. Being heat pulses, they briefly raise its temperature. The carbon resistor is quite sensitive to changes in temperature. It acts as a thermometer. So, the heat pulse of second sound creates a pulse-like change in the resistance of the disc up here. It isn't hard to convert this resistance pulse into a voltage pulse. What we will do is to maintain a small DC current in the top resistor. It is supplied from a battery in this metal box. The box shields the circuit in order to reduce electronic noise. The voltage pulse is small. In this second box, we have an amplifier. The amplifier output is fed into the oscilloscope, where it will appear on the upper trace. The horizontal timescale on this trace is exactly the same as for the bottom trace. However, the upper trace records voltage changes as they occur in the top resistor, the detector of second sound. The temperature of the liquid is about 1.65 degrees Kelvin. The battery has been turned on. And now the amplifier. Among noise and other distortions in the upper trace, a clear-cut voltage pulse appears, about 4.5 units to the right, 4.5 milliseconds later than the pulse entering the heater. This pulse in the upper trace is also about 1 millisecond long. It is the second sound as it arrives at the upper resistor. The upper trace also shows a strong voltage pulse at the left, simultaneous with the heater pulse. That's due to pickup by electromagnetic wave, with the heater acting as transmitter and the detector as receiver. We are moving the detector towards the heater. The pulse moves with it to the left. Notice the echoes of second sound which appear on the upper trace while the detector is near the heater. They are caused by multiple reflection between the two resistors. A total of 3 echoes is clearly visible. Moving the detector away from the heater increases the delay. Here we have the resistors at their original distance again. They are 9 centimeters apart. The wave of second sound covers 9 centimeters in 4.5 milliseconds. The speed of second sound is 2 centimeters per millisecond, or 2,000 centimeters per second, or 20 meters per second. Let me return to the discussion of the two-fluid model for liquid helium-2. We find that it gives us an adequate qualitative description for the behavior of helium-2. The superfluid component is frictionless and free of entropy. It is thought to be the part of helium-2 which leaks through the finest pores, which rises up toward the source of heat in the fountain effect, and which creeps up along the walls of the container. The normal component, on the other hand, is viscous and possesses some available heat energy. The normal component is thought to be that part of helium-2 which is dragged along by the rotating cylinder, and which remains behind in the beaker with a porous bottom unless it is first converted to the superfluid component. Now, a model alone is not a theory. It turns out that quantum mechanics has had to be brought to bear on the problem of producing an accurate check between theory and experiment. As is usual, when we attempt to explain a quantum mechanical system by a classical model, this model gets lost, becomes washed out, so to speak. It's there, but then again it isn't. The model is false, but many of its elements survive. That's what has happened to the two-fluid model for liquid helium-2. Helium-2 must now be considered as a quantum mechanical system. It is still true that helium-2 is capable of 2 different types of motion, but we cannot anymore claim that these 2 motions occur on different parts of the liquid or on different groups of helium atoms. Rather, we should look at it all as one liquid system capable of 2 different types of motions simultaneously. The superfluid motion, a perfect fluid flow, reversible in the thermodynamic sense, and the normal motion, a viscous flow, either laminar or turbulent, and irreversible.